Hello students, in this video we'll define divergence and Laplacian using the covariant derivative. Let's recall that the covariant derivative of a contravariant tensor is given by the following formula. It's given by partial aj, partial xi, and then for contravariant tensors it's going to be a plus gamma I j m and then a m. So this is the covariant derivative of a contravariant tensor. Okay, now what I'd like to do is I'd like to define an invariant. So I'd like to define an invariant called the divergence. And what we're going to do now is let's consider the covariance derivative of ai. So let's trace over that. So let's sum over I in this, right? So what will this give us? This is going to give us partial ai, partial xi. Again, summing over I have a one top, one bottom, so I'm summing in this case, plus gamma, and then I summing am like this. And now we use the fact that there's a special formula for when we sum the Christoffel symbols where there's one upper and one lower that are the same. It is the derivative with respect to this variable over here of the log of the volume element, right? So this is going to be partial, and we proved this in a previous video, partial ai, partial xi, and then plus d by dxm of the log of the square root of g like this, times am, of course, right? Am, like that, okay? And now, of course, we can use some calculus to simplify this over here. So I can change this m into an I over here, and we can note that the derivative of the log of the square root is going to be what? It's going to be 1 over the square root of g times the right thing, right? Because I can take this g as a power and pull it out, so we're like a 1/2. And so what we can do is we can write this as 1 over, so we claim now that this is going to be equal to 1 over the square root of g times the derivative with respect to m of what? Of root g a m like this. So let's prove this and see how this works over here. So let's check. All right, and so if we claim this formula is true, let's just do the calculus real fast to make sure this works, right? So this is going to be a 1 over root g, and then by the product rule, it's going to be a root g times partial am with respect to xm. That term is good, plus 1 over root g, and then times the derivative of that thing over there, which is going to be a what? Which is going to be a 1/2, 1 over 1 over root g. That's going to be a 1 over g times 2, perfect. And then that's times what? Times am. And so, of course, this thing over here is exactly just 1/2 of 1 over g. And so we see that that is exactly what we want. So in other words, this expression over here is an invariant position. And so this allows me to say that the divergence of a contravariant vector am is exactly given by this formula, 1 over the square root of g, and then d by dx m, square root of g am. And this defines the divergence differential operator in metric coordinates. Excellent, okay? Now you might say, well, how can I use this to define what the divergence of a covariant vector is? So the divergence of a covariant vector, aj, is just given by what? It's just given by g, I, k, and then I'm going to do a covariant derivative, a k covariant derivative of the ai terms like this, okay? In other words, I just do a covariant derivative, now I have a double trace, and so this gives me the divergence of a covariant derivative. Okay, excellent. And now how can we define the Laplacian? Well, that's one thing we're really almost always after. And so now the next thing to do is to recall a function of the variables, any function of the variables x1 through xn. Just a straight function, not depending on any indices, is an invariant. Doesn't depend on the coordinates, right? No matter where you are in space, no matter what the coordinates are, the function is to output the same thing, right? That's the basic idea. And so for an invariance, the covariant derivative of an invariant, a function f, invariant, not depending on coordinates. In other words, invariant simply means that f is equal to f bar, right? That's what invariant means. It's just simply df dxi. And of course, that's a one covariance tensor, right? So this is one covariant over here. And so I have a one covariant thing, so I can do a covariant derivative of it, right? And so now form the covariant derivative J of the covariant derivative I of this invariant F. So this is the covariant derivative J of partial F partial xi. Beautiful. And now how do you do a covariant of this thing? It's the second derivative, so remember that we have this formula over here for it, right? So it's going to be the second derivative, d squared f d x, d what? dxj dxi. And then it's a contravariant thing, right? So I have to do a minus over here. And then minus what? And then minus gamma. I need an I. And then with respect to j, what am I going to have over here? I'm going to have a j in the denominator, so I need a j over here, an m over here, and then a partial f, partial x, xm, like that. Okay? That gives me everything I want. Beautiful. And so now we're ready to define the Laplacian. So now to define the Laplacian, of f. So what will the Laplacian be? The Laplacian of f, this invariant, is going to be the sum over I and j. I'm going to do a g upper ij, this like that, of f, right? And so now all I got to do is just put the gij out in front of this thing over here, right? And then partial squared f, partial xi, xj, and then minus gamma I, j, m, partial f, xm. And I see here that there's two summations. So it actually turns out that this expression over here is an invariant. This expression is invariant. It's a trace. In other words, it doesn't depend on the coordinate systems, right? And that's why we can't define the Laplacian as we typically see in an ordinary multivariable calculus class. In an ordinary multivariable calculus class, you just say, oh, the Laplacian is easy to define. The Laplacian of a function f is just f(x(x) plus f(y)y. But we know that in different coordinates this thing changes. We've already seen it many times before that if I do it in polar coordinates, the Laplacian is this form over here, 1 over r fr plus 1 over r squared f theta theta, right? So in other words, this expression, second derivative of one coordinate plus second derivative of another coordinate, is not an invariant expression. So, and this, however, this expression over here, so in other words, what operator is involving, what operator outputs this in Cartesian coordinates, this in polar coordinates, and in different coordinate frames, it gives me different answers. And the exact answer is this thing over here, this expression over here, the metric upper, gij, then the covariant j derivative, the covariant I derivative, applied to an invariant function will give you the definition of what the Laplacian of that function is in that coordinate frame. Thank you very much.